Okay, hey everyone, this is the first lesson. So, we're going to get going with the notes and all that in just a sec. I just want to give you a little bit of a preview of what's going on. So I'm just going to share my screen with you. Okay, so you should be able to see Desmos now. What we have here is we've got a regular old parabola from pre-calc 11. This is easy to graph. What we're going to do is we're going to be looking at what the heck happens when we have something like 1 divided by 2x squared minus 4. So if you haven't thought about it at all, just take a second and try and guess, what is this graph going to look like? I'm just going to show you in just a sec. Pause the video and actually think about it. Actually do it. Okay, I'm going to assume you have, even though I know half of you didn't, but let's just go for the Optimist View. Okay, so we've all had a think about this, and when I uncover this, it's going to look like that. So if this surprises you, that's maybe good, maybe bad, doesn't really matter, but what we have here is we've got a very interesting thing. In fact, I'm going to hide the original. So we've got a graph that looks like this. Rational functions have this tendency to have these big swooping up and down, goes off to infinity things. I'll give them the name in just a sec. It also tends to avoid some points. Like you can see, this graph never really crosses the x-axis. So we're going to look at this behavior and a lot of other behavior. There's going to be a lot of new terms and bringing in some familiar concepts as well. Anyway, so let's get started with it. So, Chapter 3, Rational Functions. So, let's just take a second look at the big ideas here. I write these down just because I want you to have an idea of key things that we want to look at as we're moving through this, but there's going to be lots of information. So the big key idea here, main one, is rational functions. They're different than polynomial functions. We just spent all that time looking at polynomials, but now we're looking at rationals. What we're going to see happening here is we're going to get asymptotes and holes. And if you don't know what those things are, let's look at the next point. Asymptotes are invisible lines that a graph approaches but does not touch. I'm going to put a tiny little star because sometimes it can, but for the most part it doesn't. So if you imagine a graph gets really close to some line, you can't actually see the line, but it's there. And if we just jump back to what we were doing before Desmos, if you actually look at this, it looks like there's some invisible boundaries that this graph just does not cross over. More on that later. We can have vertical, horizontal, or even slant asymptotes. I'm going to cut this one out because we're sort of running low on time because of the week we lost. It's an interesting thing, but we'll just avoid that for now. And the main ones, really the main ones that are going to come up in the future, are vertical and horizontal ones. We're going to look at the degree of the numerator and denominator to figure out which is which. But for the most part, we're going to focus on the vertical and horizontal ones. All right, so just a quick little definition thing. I'll get to the examples in a sec. What do I mean when I say a rational function? This is one of those mathematical things that looks really intimidating, but it's basically saying a rational function is a polynomial g of x and a polynomial h of x. H of x can't be equal to 0. If you remember the non-permissible values from pre-calc 11, that's going to be an important part of this as well. So when you have the division of two polynomials, you get a rational function. Simple. Okay, so which of the following are rational functions? If we look at the top, is this a polynomial? The answer is absolutely yes. I'm going to write p of x for polynomial, and on the bottom that's also p of x because that's a polynomial as well. Remember, a polynomial just has to have integer exponents, positive integer exponents actually. So these are both polynomials, so yes, this is rational. Checks. Okay, is this one a rational function? It's definitely a polynomial. Is it irrational? You could make the argument that this can be written as over 1, and technically, if you look at the definition of polynomials, which is not super important right now, but I will tell you, 1 is technically a polynomial. It's called the constant polynomial, so yeah, this one's rational as well. This is a case of maybe like a trivial rational thing, but it does still technically qualify as a rational function. This one, if you see the square root right here, this is not a polynomial. Not a polynomial p of x. So this one is not something we're going to deal with, so this is not rational. And does it actually have a name? I have no idea, but I can tell you it certainly is not rational. Okay, so we're going to deal with graphing this kind of stuff, we're going to look at this, although this kind of looks like the last unit. This stuff is just, that's out. Okay, I'm just not going to mess this up too much. I'm erasing these things here. Okay, this is not a big part of what we're doing. Just be aware of what a rational function is. Polynomial divided by polynomial. Okay, so the main rational function is what you would call the reciprocal function, and it's simply y is equal to 1 over x. We're not always going to do 1 divided by, but a lot of times we will. So if we want to figure out what this guy looks like, we're going to look at it and we're going to make little table values. Now the values that I'm going to pick here, and you might be familiar with this graph. It was one of our 12 important graphs in the beginning, but I'd like to look at this in a little more detail. If x is equal to 0, what is y equal to? We go 1 over 0, and as you know, that is undefined. We cannot plot a point when x is equal to 0. We can do some things, though. We can plot x is equal to 1. I'm leaving a little space here because I'm going to want some other values. When x is 1, y is 1 divided by 1, which is 1. Okay, so we can actually go ahead and we can plot that. I'm going to assume each of these little marks is worth 1. Okay, we can go to 2, 3, 4, but I'm not really super interested in that. I'm going to go to 10. 1 divided by 10 equals 0.1. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Somewhere over here would be 10, and we're going to have like 0.1. Just extend that. You can see what's going to happen to my values. As I go to 100, it's going to get really small. Now the big question is this thing ever going to get to 0 as this thing continues on and on and on forever to 100? We're going to have that point get really, really, really low, but is it ever going to go to 0? And the answer is absolutely not. And I'm just going to write a little thing. As x goes to infinity, y is going to go to 0. You notice I'm not putting equal signs, I'm just putting arrows because it means going to but not equal. I'll actually write that down. Goes to but never equals. Okay, so I left a little bit of space here. If I make x is equal to 0.1, 1 over 0.1 is actually equal to 10. So when x is 0.1, we're going to try and fit it in here. And then we're actually going to be off the graph already, up to 10, but it's going to be really high. When x is equal to 0.01, then this guy's going to wind up equaling 100. And what you can see is x gets really, really, really small, like 0.0001. Then we're going to be having, well, I don't have enough room here, but you can see what's going to wind up happening. X is equal to, or sorry, y is going to be equal to what, what's that? I guess that's going to be like 10,000. You can try this. If you've got a calculator, put in as many zeros as you want after the decimal place, follow it with a 1, push equals, and the numbers are going to get bigger and bigger and bigger and bigger. When you go ahead and you graph this, you're going to wind up connecting all the points, and they're going to do something that kind of looks like this. I'm going to just sort of sketch this a little bit. It's going to go through 1, 1, and it's going to go like this, and it's going to continue on. And I'm going to put an arrow there, and I'm going to put this arrow over here. So we can also say another fact about this. As x goes to 0, y goes to infinity. We've actually got some other things to think about as well. This is half the graph. We've got all the x values that are positive. If we start doing negative values, I don't need to write all of them, but I can certainly write some of them. When x is -1, y is going to be -1. And when x is -10, this will be -0.1, and so on. What happens when x goes to -infinity? Well, y is going to go to 0 as well. So we're going to wind up getting a similar sort of situation, -1, -1 here. Let's fit that. We're going to wind up getting a graph that actually winds up going like this. Okay. Now, if I went a little faster, you sort of missed something or you don't believe me, take a second and actually plot it yourself and really think about it, because this graph's going to be very important as we move on. What I really want to emphasize here is the value of x is equal to 0 doesn't exist, so our graph never touches it. And there's no value of x we can pick so that the value of y ever exists. So when I say note key features, I'm going to point out a couple things here. The domain is a key feature, so the domain is x is all real numbers except for 0. And the range, y is going to be all real numbers except for 0. We're also going to note we have a couple invariant points. Points that when I go 1 divided by x, or I don't even go 1 divided, I just say y equals x, those are going to be at 1, 1, and -1, -1. So those are some key points that we really want to focus in on. So the points right here and right here are going to be important in the fact that it never touches either axis. Okay, so there you go. Moving on. As I sort of mentioned, this graph has no intercepts. These are the key points, 1 and -1. Invisible lines that the graph approaches but does not touch are called asymptotes. So what we say here, and this is the big idea, when we say it never touches x, we say there's a vertical asymptote at x is equal to 0. So what that means is up on my graph, I could actually draw, and you won't always do this necessarily, but you can, I could draw a vertical line just going like this along that y-axis. And I could say there's a vertical asymptote, VA, at x is equal to 0. And I can also say there's a horizontal asymptote at y is equal to 0, because horizontally, this graph never actually crosses the line y is equal to 0. So I'm going to say HA for horizontal asymptote at y is equal to 0. Okay, so those are asymptotes. They're pretty simple. The graphs get really close to it, but they don't actually ever touch it. And I did mention it's possible sometimes for it to touch, but that will be covered a little later. Okay, here's another little example. Let's sketch this graph. So if you look at this and you're overwhelmed, you don't need to be, because you just need to realize that this is a transformed y equals 1 over x graph. So what I would do is I'd, first of all, acknowledge that the parent graph is y is equal to 1 over x. Then what I would do is I would say this has some transformations. So the 2 up top, and the 3 here, and the 1 here, this can be written as the image graph is y equals, so it's like there's a 2 multiplied by my function. So I'm going to say this is like 2f of, now instead of x being in the denominator, it's x minus 3, so that's where in the argument we would write it like this. And there's a 1 added on to the end, so we would add a 1 like this. So we can think of this complicated looking thing as 2 times 1 over x, so that's where the 2 over x comes from. And we've got x minus 3 on the bottom, so that's why I put that in the argument, and then the plus 1 at the end there. Okay, so what we can say about this here is this would be a vertical stretch by 2. This is 3 to the right, and then this is 1 up. I think I got one of those in Mario once. Okay, so normally we would have a graph with some key points. So what we would do is we would say f of x, and then we would use mapping notation to turn it into 2f of x minus 3 plus 1. So any point x, y is going to move over to the point. Okay, so we got to remember this stuff. 2 times a function, that means 2 times y, that's a vertical stretch. And we're also moving it up by 1, so we're going to add 1 there. We're moving x 3 spaces to the right, so it's going to be x plus 3. Remember, x minus 3 has the opposite effect that we would expect. So I'm going to take some key points here. So normally we would have, like, I'm going to call this A, and I'm going to call this B. A is located at 1, 1. B is located at -1, -1. So A, 1, 1 is going to go to A prime. And we're going to say, let's see, 4, so 1 plus 3, 2 times 1 plus 1. Let's see, that's 2 plus 1, that's 3. And then B is going to go like this, B prime. So -1 plus 3 will be at 2. 2y plus 1, so it'll be -2 plus 1, so it'll be -1. Okay, so that's where my points are going to move to. So what I'm going to do here is I'm going to write down at 4, 3. I didn't actually write it, but we're assuming each square counts for one little grid mark. And then B prime is 2, -1, so it's going to be right here. Okay. So there's one more thing we should think about. It's not a point, but it is the asymptote. The vertical asymptote is x equals 0. Where does that go in this mapping notation? A vertical stretch and vertical translation doesn't move it, but a shift of 3 to the right, that's going to make it go to x is equal to 3. The horizontal asymptote, which was y is equal to 0, we're going to use the transformation 2y plus 1, so we're going to multiply that by 2, and then we're going to have 1, so that's going to be y is equal to 1. So when I'm drawing these things, I'm actually going to want to put in my horizontal and vertical asymptote. So the vertical asymptote is x is equal to 3, so I'm actually going to draw that in. So I say they're invisible lines, but you can definitely draw them in as dotted lines. You're just not going to make them solid. Okay, so there's y is equal to 1, my horizontal asymptote, and here's x is equal to 3, my vertical asymptote. Now we've just got to draw the graph. It is stretched by a factor of 2. It's got to rub up against these asymptotes, and it's got to go through these key points. So now I'm just going to kind of do my best to just sort of sketch it in. So I'm going to make it go like that. One could argue we might want a few more points, but to be honest, I kind of just want to know where it's going. Now, some of you might be going, well, is this as accurate as it can be? And I would say, no, it's definitely not. And in fact, the one that I just drew down here, I'm actually kind of thinking, why don't we figure out the intercepts? So another thing which would be good is to find the x and y intercepts. And that's something that's very easy to do. That's no different in this unit than any other unit. If we want the x-intercept, we're going to set y is equal to 0. So why don't we actually do that? 0 equals 2x minus 3 plus 1. So we can solve that by just isolating x. The way I'm going to do that, I'm going to take 1 to the other side. And then there's a little algebraic trick here. You can multiply both sides by x minus 3 and all that fun stuff, or you can actually just switch the positions of the -1 and the x minus 3 there. Okay, solving this, x equals, let's see, that's -2 plus 3, x is equal to 1. So that is my x-intercept. Oh, look at that. I nailed it. Okay, so I got it just by luck in the right spot, but it was helpful to get it precisely using algebra. If we want to get the y-intercept, we'll set x equals to 0. Now don't have a fit because in the original one, 1 over x, you can't make x is equal to 0, but you can totally do it in this image equation. So we're going to write y equals 2 over 0 minus 3 plus 1. Okay, so this is kind of gross because now we've got to go -2/3 plus 1. -2/3 plus 3/3 is 1/3. So that would be my y-intercept. Did I get that? Oh, geez, that's actually pretty darn close. I'm pretty happy with that. I'm going to say it's beginner's luck. Okay, so there's my graph. Looks pretty good. At some point, someone's going to say, hey, can we see this on Desmos? And I would say, you know what? That's a great idea. So let's just check our work real quick. I'll delete this. So y equals 2 divided by x minus 3 plus 1. And let's actually make it visible. And if you look at that, that's more or less what we did. On Desmos, if you want to actually draw in the asymptotes, you're going to have to put them in manually. One thing I really like to do is I like to make them dotted, and I like to make them black color. Okay, so there's my graph. Does that look like what I did? Yeah, actually pretty good, so I'm pretty happy with it. All right. Okay, there's actually another trick you can use here. It doesn't work all the time, but it's worth using. They certainly like it in your textbook, and I think it's worth seeing. Sometimes we can take something that doesn't look like a simple 1 over x parent graph transformation, and we can make it look like this standard form. So this is the standard form for a rational function, and if we can get it in this form, the transformations is really easy. If it's not in this form, we'll look at how to graph those and do all that sort of stuff, but it's a little trickier. So the way this is going to work, we're going to take an equation like this, and we're going to make it look like this. So one thing to notice here is we've got x up top and the bottom, and here we want to have it just in the bottom. This is actually not an obvious thing to do, but it's not really that hard. So the trick is this, and you need to use a little bit of brain power. It's not a follow the steps method, but most of you can figure this out with no problem, I think, with a little bit of practice. So if you notice here, we want to have something cancel. So I'll just show you how to do it, and then you can have a look at the process. For x minus 5 and x minus 2, nothing cancels there, but I'm going to use a little trick. It's not so much a trick, it's just something smart. I'm going to rewrite negative 5 as negative 8 plus 3. And then I'm going to write this as x minus 2. I haven't done anything wrong. I've rewritten this number as this. You have to agree that negative 5 is the same as negative 8 plus 3. So it's really important to understand that we are not actually changing anything, we're just rewriting it. And I'm going to use a wonderful property of fractions where I can now split this up so that I'm going to grab, kind of going to break it up, so that I'm going to use this as one fraction and I'm going to use this as the other fraction. So the way that's going to wind up looking here is I'm going to write this as 4x minus 8 over x minus 2. And then I'm going to add to it, I'm going to separate these 3 over x minus 2. If you can see where I'm going, that's great. If you can't see where I'm going, well, hold on. In fact, you might even pause the video and just see if you can take it from here if you haven't already. Okay, so what we're doing here is I picked negative 8 and 3 because I could see that 4x minus 8 and x minus 2 have a common factor. I can actually factor a 4 out of this, and I can write it this way. I can't do anything with this other one, but that's okay. I don't really need to. The beautiful part here is I can actually look at this, and these can actually cross out. So this can be rewritten now as 4 plus 3 over x minus 2, or if I want to really make it look like my standard equation, I can write it as 3 over x minus 2 plus 4. That is a much more helpful way of looking at this equation. And now, I'll come into my own wires here. Now I can actually graph this. One thing, someone might have a little bit of a fit and say, I thought there's a non-permissible value here when x is equal to 2. You can't cross those out unless you write that. You'd be absolutely correct. But you know what? That's actually not going to be an issue because we're going to see here, this is going to tell us that we have a vertical asymptote when x is 2. So our graph's never crossing that point anyway. Okay, so what we're going to do is we're going to look at, again, the main type of graph. The parent would be this guy here. I don't even really want to draw it. I'm just refreshing us. That's y is equal to 1 over x. And what we're going to do is we're going to transform it. So if we look at what are the transformations here, I'm just going to get rid of that because I don't want to clutter up my graph. The transformations are going to be this guy here. That's my vertical expansion by 3. This means I go 2 to the right. And this means I go up 4. So some key points here, what I've been calling the point 1, 1 for A, and B is negative 1, negative 1. These are going to move, so we're going to do the same thing before. In fact, we can write the general mapping notation. Vertical expand by 3 and up by 4 means that y is going to turn into 3y plus 4, and x is moving 2 to the right, so it's going to be x plus 2. So, oopsie doodles, too many brackets. So the point A at 1, 1 is going to turn into, let's see, 1 plus 2 is 3, 3 times 1 plus 4 is 7, and then this one's going to be negative 1 plus 2, so 1, and 3 times negative 1 plus 4 will be 1. I hope I don't make any stupid mistakes, and none of you are able to call me out, so if I do make a silly mistake, I guess you'll have to leave it in the comments, and if the comments are disabled, whoops. Anyway, okay, so I think this is all correct. Desmos will use that to check it anyway if I did make a mistake. Okay, so anyway, so let's see here. We've got 3, 7, and 1, 1. So I'm going to again assume each one of these is worth 1 mark each. 1 value, not marks. So this is the point A comma prime at 3, 7. And B prime is going to go to 1, 1. So there's B prime at 1, 1. Okay. What happened to my asymptotes? Normally, the vertical asymptote x is equal to 0. That is going to go, let's see, so we're taking x values and we're moving them to the right. So x is equal to 2. And the horizontal asymptote y is equal to 0. We're going to move that over to 3 times 0 plus 4. So I'm going to actually draw here. So now this is where I'm having a little bit of a, I see I made a mistake. I knew it. See, I wrote 3, 7 here. I meant to put it up here. 3, 7. If you're keeping track of your own brownie points at home, if you notice I made a dumb mistake like that, give yourself a mark. Okay, so when y is equal to 4, that's my horizontal asymptote. It's going to go across like this. And when x is equal to 2, that's my vertical asymptote. I was having a bit of a heart attack because I knew the asymptotes had to go halfway in between those key points, and that wasn't happening. That's how I knew I made a mistake. Okay, so now we're going to plot the graph. Everything else is pretty standard. We haven't reflected or done anything weird like that, so we're just going to go ahead and we're going to draw some points. I don't super care about getting the shape perfect. I just want the rough idea. We can easily get the X and Y intercepts. In fact, we might as well do that. The Y intercept here will solve for it. Again, we're going to make X is equal to 0. So Y equals 3. 0 minus 2 plus 4. Oh, so that's negative 3 over 2 plus 4. What's that? Positive 5 over 2. So that's at about 2.5. So I'll mark a point right there. And the X intercept, I guess I'll shove over here somewhere. We're going to set y is equal to 0, and we're going to solve. So that is 3 over x minus 2 plus 4. Take the 4 over, and then we'll do the little switcheroo. Okay, so x is equal to negative 3 over 4 plus 2, which is what, 5 over 4, I believe. So that's just a little greater than 1, so maybe like here. Oh, and that's looking really good. So all my points are going to go through here, and I'm going to draw arrows, and you're really going to do your best to show that it's getting close, but not touching those asymptotes. Okay. Last example. Okay, if you have not paused the video to try this yourself, do it. So what I'm going to look at here is I'm going to look at this equation. I'm going to say I really want to get something canceling, so I want the top to cancel with the bottom. 2x plus 1 and x plus 1, they do not cancel. I swear, if anyone does this and says it's equal to 2, I'm going to lose it. Yeah, I'm going to know if people do that or not. Okay, so what are you going to have to break this top up into to turn it into something useful? And it's going to be 2x plus 2. Of course, we can't turn 1 into 2 for free, so 2 minus 1 is 1, and everything's all balanced and good. Okay, now we can split this up into 2 different equations. Sorry, not 2 different equations, but 2 different parts. The denominator stays the same on both parts, and what we can see is for this first guy here, we're going to have that. These guys will cancel out, and you're left with 2 minus 1 over x plus 1. Okay, we're going to write this in the standard form, which means I'm going to put this first, and I'm going to write 2 at the end. Okay, so this is pretty similar to the last one. You'll notice there's one big difference, and we've got this guy, which is a reflection. Because the negative sign is not with the x, we're going to treat this as a vertical reflection. this is 1 to the left, and then this is up by 2. So this means our mapping notation is actually going to look like any point x, y is going to map to, let's see, so we're not going to do anything reflection-wise to the x, but we are going to move this 1 to the left. We're going to flip the sign on y, so we're going to make a negative y, and we're going to add 2 to it. So the point A, which is 1, 1, and B, which is negative 1, negative 1, that's going to turn into, let's see, 1 minus 1 is 0. Negative 1 plus 2 is 1. Negative 1 minus 1 is negative 2. Negative 1, okay, I got to make sure I'm doing this right. Negative y, so negative 1 is 1, plus 2 is 3. The vertical asymptote, x is equal to 0. That's moving to x is equal to negative 1. And then the horizontal asymptote, y is equal to 0. It's going to move over to y is equal to, let's see, negative y plus 2, so just 2. So we plot these points. 0, 1 is going to be right here for A prime. B is going to be negative 2 and 3. This is looking weird, but I think it's going to work out. X is equal to negative 1 is my vertical asymptote, so I'm just going to clear this out. X is equal to negative 1. And y is equal to 2. It's going to go across like this. Great. So normally these graphs have been doing this kind of swoopy thing, but I have to remember I vertically reflected. So instead of that, it makes sense that A is now below the graph here, and B is above. So not below the graph, I mean below the asymptote. Okay, again, I keep putting that A in a bad spot. Anyway, you get the idea. One thing we have not done, of course, is we have not solved for the intercepts. We know the y-intercept because that's where A landed, and x is equal to 0 and y is equal to 1. But what's the x-intercept? Why don't we actually figure that out, because that's easy enough. So we're going to set y is equal to 0, and we're going to solve this. So what we're going to do is we're going to move 2 to the other side. I'm going to just get rid of those negative signs. And we're going to do the old switcheroo, so x plus 1 is equal to 1 over 2. And we're going to subtract 1 from both sides, so x is equal to negative 1/2. And I didn't quite get that perfect, so maybe I'll just move that point over just a touch. There we go. Okay. There we go. Ta-da! Now I said we'd go to Desmos and we'd check, and we better do that, because I already caught myself making one little mistake. So the last graph we just had, we had, let's see, negative, why is my memory so bad? Negative 1 over x plus 1, and then we have a plus 2 at the end. Is that correct? Yep. So there's my graph. Does that look similar to what we have? I believe so. And then the other one was 4x minus 5 over x minus 2. 4x minus 5. Okay, gotta make sure we just type it in right. I realized for this one I went back to the original equation instead of what I simplified it down to, but whatever, it's all good. Okay, there's my point 3, 7, which I screwed up, but it looks like the graph is now matching what I've done. Crosses over at the correct points, 2.5 and 5/4. So, looks like we're pretty good. Okay, so that was the first lesson. Didn't go too bad. If I did anything weird or confusing, feel free to ask. We'll talk about how you can get a hold of me, definitely in-person meetings, email, and if the comments are working, you can always try and leave a comment and you guys could actually discuss it. Anyway, thank you, and I'll see you guys later.